Okay, so in this section we're going to look at inequalities. Inequality symbols come in 4 general flavors. This way, this way, this way, and this way, right? So less than, greater than, less than or equal to, greater than or equal to. For instance, we could have the statement, x is less than 2. So this is representing all values that are smaller than 2. We can have x is greater than 2. This is representing all values that are strictly greater than 2. X is less than or equal to 2, or x is greater than or equal to 2. So the difference between those and these is that we actually include the actual point of 2. So we can represent these this way. So we can also represent them this way. So x is strictly less than 2 can be represented on a graph, a number line, where the solid blue arrow is pointing to the left, going out to infinity. Notice there's a little open circle at the 2. That indicates for us that we don't actually include the number 2. So the solution set, the values of x that I can put in here to make this a true statement, I can put in a 1, I can put in a 0, I can put in a 1.2, I can put in a 1.99999, that's also true, but you can't put in a 2, right? Starting at 2, this makes it a false statement. For this one, less than or equal to 2, well then now we include the 2. So we put a solid dark circle at the 2 to indicate that we do include the actual number 2. Good. So we can describe it with a graph, or we can also use interval notation. Notice that for interval notation, in this case for instance, this would be described as negative infinity up to 2, and we put parentheses this way to indicate that we don't actually include the 2, whereas over here this would be described as negative infinity to 2, and then we put brackets around the 2 in order to indicate that we definitely do include the 2. Good? Questions on the notation? Notation? Okay, so the way we interpret this, remember that the little open mouth of the inequality is always supposed to be facing the largest number. So on the number line, we have 0, we have 1, we have 2, we have 3, we have 4, Numbers are always going to get larger in that direction. Larger that way. So we would say that 3 is greater than 1. We can read it this way, 3 is greater than 1. We can also read it that way, 1 is less than 3. So as you're reading, if you run into the tip first, then you say less than. And as you're reading, if you run into the mouth first, then you say greater than. 3 is greater than 1, or 1 is less than 3. We can also reverse that and write it this way. And we express the same thing, 3 is greater than 1, or 1 is less than 3. So we can write it in each direction. But we have to be careful that the little mouth guy is always facing the larger number. And that's easy, I think, with the positives, but it gets a little confusing with the negatives. So with the negatives going in this direction, we maintain the same statement. Larger numbers go that way. So we'd say that negative 1 is larger than negative 2. Negative 1 is larger than negative 2. Seems a little weird. Think of it as debt. Someone that owes $1,000 is wealthier than someone that owes $2,000, right? You're closer to being out of debt, so you're wealthier. So negative 1 is larger than negative 2. Okay, they stay in this direction. Good. Okay, so that's something to keep in mind. Properties of inequalities. The first property is the addition property. It's easy, it's straightforward, it makes sense, it stays in line with everything we intuitively know about algebra. So, for instance, consider this. If we have 5 is less than 7, definitely true, right? No questioning that. 5 is less than 7. And what we could do is that we can choose to add or subtract any constant to this. Like 5 is less than 7, but maybe you choose to add 2 to this side, add 2 to this side, which means that over here we end up with 7 is less than 9, also true. Good. So we can add something to both sides. Or we can also subtract something from both sides. Instead of adding 2 from both sides, I could choose to subtract 2 from both sides. -2, -2, and now in this case I would end up with 3 is less than 5. Also true, right? So you can choose to add or subtract anything you want from both sides of the inequality, and if you start with a true statement, you end with a true statement. Okay, well, this is obvious when we have all these numbers like this, but if we had some variables, like if we were given that A is definitely less than 5, then we don't question that. That's given to be true, so we start off with that being true. And now we can choose to add or subtract anything we want to both sides of the inequality. So maybe I decide that I want to subtract 11 from this side. I want to subtract 11 from this side, less than 5 minus 11 from this side. I'm subtracting the same quantity from both sides. On the left-hand side, there's no way to simplify that since I don't know what A is. So I just end up with A minus 11. And on the right-hand side, I get negative 6. So A minus 11 is less than negative 6. And I must now conclude that that is also true. I started out with something that was definitely true. I subtracted the same quantity from both sides of the inequality. Therefore, I end up with an equality that's also true, right? Thereby giving me one of those great algebra statements, right? Whatever you do to one side of the inequality, you must do to the other. You maintain the inequality. If we know that A is less than B, right? If this is known to be true, then we know that A plus C is less than B plus C. That's also going to be true. And that doesn't matter whether the C is positive or negative, right? We can add or subtract any value C, or add a positive or add a negative C to both sides of the equality, and everything stays the same. Okay? All right, now consider what happens if we have multiplication. Well, if we have, for instance, again, a true statement like 4 is definitely less than 10, then I can choose to multiply both sides of the equality by 3. I'm going to multiply this side by 3, less than, multiply this side by 3. And so I end up with 12 is less than 30. Right? I started out with something that was true. I multiplied both sides of the equality by 3, and I end up with something else that's also true. Right? So that looks good. But note what happens if we multiply by a negative. So 4 is less than 10. If we multiply this side by negative 3 times 4, less than negative 3 times 10. On this side, we end up with negative 12 is less than negative 30. And remember, on the number line, it's going to be false, right? So here's the number line. Here's 0, 1, 2. Numbers get larger that way. Negative 1, negative 2, negative 3, da 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 da. We're going to run into negative 12 first, right? And then da 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 da. Then we're going to run into negative 29, negative 30 over here. So numbers, this should be larger than this one. You're closer to being out of debt when you're at negative 12. So this is a false statement at this stage. So we started out with something that was true. And if you choose to multiply both sides of the equality by a negative, we end up with something that's false. So in order to make it true, we got to change the direction of the inequalities. So negative 12 is greater than negative 30. This is true. And that's the rule we have to keep in mind for inequalities. If you choose to multiply by a negative number, you got to change the direction of the inequalities to maintain a true statement. Good? Good, good, good? Okay, so one more thing to keep in mind. Multiplication and division are closely related. And so it's really the same rule. So for instance, if I have this again, you could choose to divide both sides by a half, divide both sides by 2. So this divided by 2. I could decide to divide this side by 2, decide to divide this side by 2. Well, dividing both sides by 2 is the exact same thing as multiplying both sides by a half. Right? Dividing it by 2, multiplying it by a half, they're the exact same thing. So the rule stays the same for both multiplication and division. Right? Dividing by 2, multiplying by a half, they're the same thing, right? Okay, so it's going to be the same rule. And the general rule is this: if we have a positive value c, then if c is positive, if the thing that we are going to multiply by is a positive number, then if the original statement is true, this is a true statement, whatever that's happening here, this is true, then we can multiply AC and we know that it's going to stay the same this way, right? This is also going to be true. That's what that's saying. On the other hand, if C is negative, then if A is less than B is true, then AC is greater than BC, right? So we change, the only thing that's different here is that we change the direction of the inequality. Good. So if C is positive, then when you multiply both sides of the equality, the direction of the equality stays the same. If, on the other hand, C is negative, if you're choosing to multiply or divide by a negative number, then you got to change the direction of the equality. And that's really the only rule you have to remember when you're solving these inequalities. Okay, so it's all the same rules of algebra. Distribution, combine like terms, add and subtract. Your goal is to isolate one of the variables on one side of the inequality. All the same rules of algebra, except one additional rule, which is really this one. Whenever you multiply or divide by a negative number, you got to change the direction of the inequality symbol. Good? Questions, comments, issues? Okay, let's try and solve this one then. Solve for x. So it's an inequality symbol. We treat this the same way as we did when there was an equal sign in almost all respects. Distribute, combine like terms, move terms to one side of the other. We keep that golden rule of algebra: whatever operation you do to one side, you must do to the other. Everything's the same, except we have that one additional rule we have to keep in mind. If you choose to multiply or divide by a negative number on both sides of the inequality, then you got to change the direction of the inequality. So well, with all problems in math, but in these kinds in particular, it's really important to stay really clean and neat with your writing. Make sure that you maintain these inequalities right underneath each other so you can keep track of the direction. If you start working that way, it's going to get really confusing, right? So some people start working this way as, I don't know, I don't even know what they put here. Negative 10x minus 20 plus 1 is less than, right? That's just going to get really confusing if you start working that way. So don't work that way, work down. Keep your inequalities nice and neat, straight, right underneath each other. In some cases you might need to flip it in the other direction, so keep that in mind. Okay, so the first thing I do is distribute this guy, right? Distribute, combine like terms. Distribute. I end up with negative 10x minus 20 plus 1 is less than or equal to 3x minus 3, nothing to do over there. I'm going to combine these two. Negative 10x minus 19 is less than or equal to 3x minus 3. Then I'm going to move this over here. Minus 3x minus 3x. I end up with negative 13x minus 19 is less than or equal to negative 3. Right? This turns into negative 13. These cancel. I'm going to add 19 to both sides. Plus 19 plus 19. These cancel. So I end up with negative 13x is less than or equal to positive 16. Notice that so far the things I've chosen to do is to subtract 3x from both sides and to add 19 to both sides. We keep the same direction of the inequality so far. We haven't changed it at all. The only time you change it is when you choose to multiply or divide by a negative number, which is what I'm going to have to do now. Right? Some people can look at this and go, divide both sides by negative 13. Okay, change the direction of the equality. Or you might think multiply by negative 1 over 13 on both sides of the equality. Same thing, change the direction of the inequality. Okay, so we're gonna take negative 13x less than or equal to 16. I'm going to divide this side by negative 13, divide that side by negative 13. That's when I gotta change the direction of the inequality. Okay, so I end up with x is greater than or equal to negative 16 over 13. Questions? Questions? Okay, let's solve this one for p. So again, keep this neat. We want the inequalities right underneath each other. We got all the same properties that we had before with an equal sign. Distribute, combine like terms, move terms by adding or subtracting, divide. Okay, so let's simplify this. We're going to have to distribute this minus 6. So we get 3p minus 24p. Don't forget that this is a plus minus 6, plus negative 6, you can think of it. Minus 18 plus 4 is less than 10p minus 35 minus 4p. We keep the direction in the same, facing the same direction, right? We haven't done anything across the inequalities. So combining like terms, I get 3p minus 24p. It's negative 21p. And I get minus 18 plus 4, that's minus 14, less than. And then here we get 6p minus 35. Okay, so I'm going to subtract 6p from both sides. 6p minus 6p. I know these will cancel. And here I end up with negative 27p minus 14 is less than negative 35. Right? All I did is subtract 6p from both sides, so I maintain the inequality. Then I'm going to add 14. So I end up with negative 27p is less than negative 21. Good. And then finally, I'm going to decide to divide both sides by negative 27. So negative 27p. No, actually, I will just put it up here. Negative 27p is less than negative 21. So I'm going to divide this side by negative 27, divide that side by negative 27. Therefore, I got to change the direction of the inequality. And so my final answer is p is greater than 21 over 27. So we could reduce that a little bit, right? 7 over 9. Okay, so p is greater than 7/9. And they're both divisible by 3. See some weird faces. I'm saying 7 times 3 is 21, 9 times 3 is 27, 3's can cancel, and so p is greater than 7/9. That's our answer. Good? Is that smaller or bigger than 1?
Small.
A little bit smaller, right? If it was 9 over 9, it would be 1, right? If it was 8 over 9, it would be really close. We're 2/9 away from completing 1. So if I wanted to draw this on a graph, number line, you know, a number line of p's, here's p, here's 0, here's 1, here's 2, here's 3. The solution is all numbers that are a little bit like close to 1, not quite there. So if we break this up into 9 pieces, 1, 2, 3, 4, 5, 7, 1, 2, 3, so there's 9 of them in there. Then here is 7/9. And so we put a circle there to show that we don't include the 7/9. And then it's all those values that are in that direction. Right? So this is like a pictorial description of that. All numbers that are greater than 7/9. Right? 1/9, 2/9, 3/9, 4/9, 5/9, 6/9, 7/9, 8/9. Of course, this one is 9 over 9. The 1 is 9 over 9. And so that way, all of these numbers going in that direction are the solution, the graph, right? Going out to infinity. We can check it by trying out our solution. Well, it's not really a confirmation. It's not going to prove that it's right, but at least it'll give you some peace of mind. Because if any of those numbers are the solution, then we can pick any one of those, go back to the original question, plug it in, and verify that you really do get a true statement. Okay? So if you get to pick any number you want, do you want to pick the number 1.275? Do you want to pick the number 2.4675? No? What would be a good one to try? How about 1? 1 is part of the solution set. It's a nice, easy, round, small number. It'd be nice to come back up here and check that if, in fact, if we replace those p's with a 1, we should get a true statement. Okay, so let's check that real quick. So, oops. Check p equals to 1 is a solution. So 3 times 1 minus 6 times 4 times 1 plus 3 plus 4 should be less than 5 times 2 times 1 minus 7 minus 7 minus 4 times 1, right? So 3 times 1, 4 times 1, 2 times 1, 4 times 1. Okay, let's make sure that this is in fact a true statement. Well, this is just going to be 3 minus 6 times, that's going to be 4 plus 3 is 7, plus 4 is less than, this will be 5 times 2 minus 7 is negative 5, minus 4. So this would be 3 minus 42 plus 4 is less than negative 25 minus 4. So this would be 3 minus 42, what is this? Negative 39 plus 4 is less than negative 29. And this will be negative 35 is less than negative 29. True. This doesn't absolutely prove that you found the right answer, but at least it shows that you're on the right direction. You picked out one of the values in your solution set, and it worked out. So you're maybe a little bit more confident that things are going well. You know, it's not absolutely guaranteed that it's correct, but you're in the right direction. If it showed us it was a false statement, then we'd know for sure that we got the wrong answer. Okay? So the check lets you know when you got the wrong answer, but it doesn't really let you know when you have the right answer. All right, let's work on this one now. Solve for x. There are two main ways that you can choose to move forward with this. They're both good. It depends on whichever one makes more sense to you. So I'll just put them as options here. Option number 1, what could you do? One thing we could do is to make sure all the denominators are the same, so we need a least common multiple between 15 and 10. Is it 150?
No. 30.
No. It's 30, right? 150 is a common multiple, but it's not the least common multiple. The least common multiple in this case is 30. Alright, so let's make sure both fractions have the same denominator so that I can go ahead and add these fractions, right? I need to have the same denominator for me to be able to add fractions. So I'm going to have 4x minus 7 all over 15 plus 2x minus 3 all over 10 less than 2/5. And I'm going to multiply this by, so I'm going to multiply this one by 2 over 2 and multiply this one by 3 over 3. That way, I can guarantee that both denominators are going to have a 30. In the numerator, I'm going to have to distribute, so I'll end up with 8x minus 14 all over 30 plus 6x minus 9 all over 30 is less than 2/5. And now that we have two fractions with the same denominator of 30, now I can combine them. One big happy fraction. 8x minus 14 plus 6x minus 9 all over 30 less than 2/5. And now what would you do?
Combine like terms.
Combine like terms. So this is going to lead to
14x minus 5.
14x minus 5 all over 30 is less than 2/5. Now what?
Wait, I think there's a mistake.
Oh, did I
It
mess
should be a
up?
plus
The ne-
9.
Yeah, positive 9.
Because yours is minus 3. Mine's plus.
Oh, the original question.
Yeah.
Oh man. Okay, sorry. The original question has a plus 3 there. Means this is a plus 3, which means that this is a plus 9. I mean this is a plus 9, which means that this is a minus 5. Oh, see, I knew that. Good. Sorry. Okay, so now what we do?
Multiply by the reciprocal.
Multiply by the reciprocal, close. We're trying to isolate the x, so I like to get rid of that guy right there. So how about if we multiply by 30 to get rid of that, right? So I can isolate my x. So I'm going to multiply this side by 30, multiply this side by 30. These guys cancel. I end up with 14x minus 5 is less than, and now how do you deal with this? Let's put a little 1 there. These guys reduce, we get a 6, and that ends up with 12. Good? Questions, comments, issues? Questions, comments, issues? Okay. Alright, so now we just add 5 to both sides. Plus 5, plus 5. We get 14x is less than 17. And then we divide both sides by 14. Divide by 14, divide by 14. And I get my final answer is x is strictly less than 17 divided by 14. Good? Questions, questions, questions? What two whole numbers is that trapped between? It's bigger than what whole number? 1, but less than what whole number?
2.
It's trapped between 1 and 2, right? It's some decimal number, 1 point something between 1 and 2. And I want all numbers that are strictly less than that. So if I wanted to check this, what would be a nice whole number for me to use to see if it works? 1 would be even better.
0.
0, right? You think about the number line? Here is 0, here is 1, here is 2. This answer is somewhere in the middle here. Open circle, and it goes this way, going in this direction, right? Forever, -1, -2. So if I get to choose any number in there, 0 is a pretty good one, right? So if I go back up here and make this 0 and make that 0, does it in fact give me a true statement? So if I have 4 times 0 minus 7 divided by 15 plus 2 times 0 plus 3 divided by 10, is that in fact less than 2/5? 0, 0. Well, that makes that easy. That's just going to be -7 over 15 plus 3/10 is less than 2/5. Is that true? Okay, common denominator is going to be, again, we could do the same thing. Common denominator of 30. So multiply this by 2 over 2, this by 3 over 3. Well, since this guy's going to be 30s, I might as well make that 30 as well, so that I have an easy comparison. So multiply that by 6 over 6. So this is going to be -14 plus 9 all over 30 is less than 12 over 30. Is that true? It's going to be -5 over 30 is less than 12 over 30, right?
Yeah.
Yeah, that's true. A negative number, the left-hand side one is going to be a negative number, the right-hand side one is a positive number. So yeah, that's true. Good, good, good. Okay, so that was option 1. Option 1 was, let's make all of these guys have the same denominator, in this case 30, so I can go ahead and add them together, bring them together as one big happy fraction, and then be done with it. The other option, let's go with option 2. We have 4x minus 7 over 15 plus 2x plus 3 over 10 is less than 2/5. Okay, so call this option 2. Option 2 is going to be to realize that, well, we could just get rid of all those fractions to begin with. by multiplying both sides of the inequality by the perfect amount. And what would that amount be in this case? We multiply this side and multiply this side by 30. The least common multiple of all three fractions is 30. So 15 goes into 30, 10 goes into 30, 5 goes into 30. That's what makes it special. It's the least common multiple of 15, 10, and 5. So when we distribute on this side, we end up with 30 times 4x minus 7 over 15 plus 30 times 2x plus 3 over 10 is less than, and I'll leave this alone for now, times 30, like that. Okay, so now 15 goes into 30 twice, 10 goes into 30 3 times, 5 goes into 30 6 times, right? Because all we did is put a little 1 underneath the 30. That's how we multiply fractions, times the whole number, put a little 1 underneath the whole number, we've got multiplication of fractions. So now we distribute here, we end up with 2 times 4x minus 7 plus 3 times 2x plus 3 is less than 2 times 6. We distribute. We end up with 8x minus 14 plus 6x plus 9 is less than 12. And that gets us to the same result that we had in the previous line over there. Okay, so combine these guys here, we end up with 14x minus 5 is less than 12, and that's the same as before. Same as before. Right? Add 5 to get to 17, divide by 14, we're going to get that x is less than 17 over 14. Good? Questions? Okay, so the other thing we're going to run into in this section is three-part inequalities. A three-part inequality looks like this. This is an example. 3 is less than or equal to x, which is less than or equal to 7. This is combining two inequalities into one single statement. It's saying that 3 is less than or equal to x, less than or equal to 7. It's combining that part, x is less than 7. Look at all the numbers where they're smaller than or equal to 7. And also combining that part where x is greater than or equal to 3. All the values that are greater than or equal to 3. So if we wanted to think about those values, we can describe it with this graph, right? The blue part is indicating all the values that solve this. It's all the values in between. I like to think this as the values in between 3 and 7. Good? Notice that we include the endpoints. That's why we put those solid blue dots in the ends there to show that we include the endpoints. So anything trapped in between. Also notice that 7 is bigger than 3, so we always put the big number on this side. So big, small, with the variable in the middle and the inequalities facing the big number. Okay, so small, big, and then the inequalities, the open mouth of both inequalities facing the larger number, or the little arrow part pointing to the small number, however you like to think about it, and the unknown quantity in the middle. We can express it this way, or we can also express it this way. Same thing, where we have the true statement of the smallest one is over there, the biggest one's over here, and both inequalities are pointing toward or facing the larger number or pointing toward the smaller one, right? So both of these are true. Both are true, but we really like this way more than anything. So more often than not, you see it this way. It's sort of the standard form of putting the biggest number on the far right, the smallest number on the far left, both inequalities facing that way, the unknown quantity in the center. Okay? Some other things that are not true. So for instance, what if we have this? What's that saying? Give me all the numbers that are bigger than 7, but also bigger than 3. Like 10. 10 is bigger than 7, and 10 is bigger than 3. Yeah, 10 works. How about 13? 13 is bigger than 7. Oh, okay, well, when you satisfy that condition, bigger than 7, you're automatically solving that condition. So in this case, this part just doesn't do anything for you. It's just attached there, but anything that solves that solves both of them, right? So it's redundant. This is just x is greater than or equal to 7. Right? This describes the same solution set as that one, so why would you write it this way? Good? Another weird thing, how about this way? This is saying all the numbers that are less than 7, but also all the numbers that are less than 3. Okay, again, this is redundant. This part right here is enough. X, all the numbers where x is less than or equal to 3 will solve both of them. Like 1. 1 is less than 7, and 1 is less than 3. Yeah, that's true. Right? So, you don't need to write it this way. We wouldn't write it this way. What else can happen? So all the numbers that are greater than 7, but smaller than 3. Smaller than 3, but greater than 7. No solutions, right? Okay, so there's a couple of variations that just don't make sense. You have to be careful with them. Either one of these two do make sense, and traditionally we like to stick to that one. Good? Okay, so when we're working with three-part inequalities, we keep all the same rules as before. You can add, subtract, multiply, whatever you like. Whenever you choose to multiply or divide by a negative number, you got to change the direction of the inequality. And since you're really working with two inequalities at the same time, you end up getting three parts. 1, 2, 3. That's why they call them three-part inequalities. And whatever operation you do to one of the parts, you must do to all three parts when you're attempting to solve these. Okay, so for instance, let's solve this one. 3/4 is less than or equal to 1 minus 1/4 x is strictly less than 3. Okay, so how do we solve this? So there's three parts to this inequality. There's this part, there's this part, and then there's that part. So whatever operations you do to one, you must do to all three parts. Your goal is to get the variable by itself in the center of the inequalities, so you can trap it and say that the answer is between two results. Okay? So we want to focus our attention to the middle one, and that will guide us to let us know what we want to do. We want to get the x by itself in the center. So with that in mind, what should we do first? Deal with the minus 1/4 or deal with the 1 over there? Deal with the 1, right? Okay. So we need to subtract 1, minus 1, minus 1, minus 1. So I'm going to have a subtraction of fractions over here. I'm going to do that on the side. We got 3/4 minus 1. So that'll be 3/4 minus 4 over 4 if I choose to multiply this by a 4 over 4 to get a common denominator. And so this will be equal to negative 1/4. Okay. So when I subtract 3/4 minus 1, this is equal to negative 1/4. Less than or equal to, well, these guys cancel. We get minus 1/4 x, strictly less than 2. And I maintain the same direction of the inequalities the whole time because I subtracted by 1. You only change the direction whenever you choose to multiply or divide by a negative, which is what we're going to have to do now, right? So some people think of this, well, let's divide by negative 1/4. That'll do it. Or you can also choose to, what's the same thing? Divide by 1/4 or multiply by 4 over 1, the reciprocal, sure. And we need it to be positive at the end. So we're going to multiply this by negative 4. Negative times the negative, this will give me a positive. And then it's really 4 over 1, so that it's multiplication of fractions, the reciprocal of this number. So whatever you do to one side of the one part of the inequality, you must do to all three parts. So we've got to multiply all three parts by negative 4 over 1. Well, here, the 4's and the negatives cancel. This is just going to give you 1. And then this way, these cancel to give you an x. And then this way, these cancel to give you that. And what am I missing? You got to switch the direction of the inequalities. This has to go that way. and this has to go that way because I chose to multiply by a negative, so these guys should face the other direction. Okay, so the smallest one is on that side, the biggest one's here, and all the inequalities are facing the larger one or pointing to the small one. That's fine. So this is an acceptable format for the three-part inequality, but really we prefer the other way. So let's write the negative 8 over here, less than x, less than 1. Right? So these two things are equivalent. We just like this one better. 1 is bigger than negative 8, so 1's over there, smallest one over here, all the inequalities facing the largest one. Oops, I lost the equal to here. There we go. Okay, so it's all the numbers trapped between negative 8 and positive 1. That's the solution. We can do that on a number line by expressing it this way. Here's our number line. Here is 0. Here is 1. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. Here's negative 8. And we want to put an open circle around the negative 8. Because we don't want to include the negative 8. But we want to put a solid circle around the 1. We do include the 1. And it's everything in between. All of these values in there are part of the solution. So if I wanted to check this and kind of decide if I'm getting the right answer, what would be a good choice for me to test this? How about 0? That makes it a nice convenient choice. If I plug in a 0 into here, that gives me a 1 in the middle. Is it true that 1 is bigger than 3/4 but less than 3?
Yeah.
Yeah, okay. That doesn't prove that this is the right answer. It just shows that one number in my solution set worked out. It doesn't really prove it, but it would prove it the other way. If I tried 0 and it didn't work out, then I definitely know something's wrong with this, right? Okay, so I can write it that way, or I can also write it in interval notation as this, negative 8 and 1, like this. And we put parentheses there to show that we don't include the negative 8, and a bracket there to show we do include the 1. Okay, one budget office rents pickup trucks for $39.95 per day, plus 19 cents per mile. One U-Haul location charges $19.95 per day, plus 49 cents per mile. Part A, find models that describe the one-day cost of renting a pickup truck for these companies. Okay, so let's see. Let's use B for budget. For budget, what kind of an equation? We have a fixed cost of $39.95, right? If you rent it, doesn't matter what you do with the truck, you owe them $39.95. But if you're going to rent it for one day and you get back at the end of the day and you turn in your truck, they're going to charge you the $39.95, and they're also going to charge you 19 cents per mile. So how can we describe that?
Plus 0.18.
So cost of the budget rental is going to be equal to $39.95 plus 0.19 times the distance that you've traveled, right? The number of miles that you've traveled. So if you traveled 1 mile, it would be $19.95 plus 19 cents. If you traveled 2 miles, it would be $39.95 plus 38 cents, so on and so forth. This is cumbersome over here, right? Cost of budget rental. So how about if we just write it as B of D is equal to 39.95 plus 0.19 D. That looks an awful lot like a, what kind of an equation? Linear equation, right? What's the slope? 0.19. What's the y-intercept? 0, 39.95, right? So this means that even if you traveled 0 distance, you still owe them 39.95. And the slope being 19 cents, that means that for each additional mile that you drive, your total bill will have an additional 19 cents. Right? For each additional mile, the bill will be an additional 19 cents. Okay? What about the U-Haul one? So the cost of a U-Haul for 1 day, a 1 day rental. Well, that one is $19.95 plus 0.49 times D, where D is the distance that you traveled in miles. Make sure that the units match. Okay, and again, this whole sentence is kind of weird. Let's just go with h of D. So this is a function where you plug in the distance in miles, and the result will be your total bill for renting the truck for 1 day. Right? If you went 1 mile, then they would charge you at the end of the 1 day $19.95 plus 49 cents. If you went 2 miles, they would charge you $19.95 plus 98 cents, and so on and so forth. Okay, so we answered part 1. Find models that describe the 1 day cost of renting a pickup truck from each location. Which one is better? Which one's the better answer? Which one should you rent? The answer depends on how far you travel, right? Life is complicated. There isn't a simple answer saying, well, budget's always better or U-Haul's always better. It depends. So if you are moving 2 blocks away, right? You like your neighborhood, you're happy where you are, but for some reason your landlord told you they're selling the house, so you got to rent someplace new, and oh look, there's one place right down the street. We get to stay in the same school system and all that, whatever. You like that neighborhood, so you're not moving far. Which one would be the better choice if you're not moving far? U-Haul, right? Because you expect that the D will be really small, and so you'll have a fixed cost that's little, and you're going to add, not too much to that because you're expecting D to be small. So if you're not moving very far, U-Haul seems like a good choice. On the other hand, if you're moving from Santa Barbara to San Diego, that's a pretty long distance. And add to that, let's say you have a lot of stuff, so you're going to make like 2 or 3 trips in 1 day. That's a lot of miles. So in that case, that might be better, right? Because your D, your distance when you come back to turn the truck in, it's going to be a big D value, so you want to make this as small as possible. Right? Okay, so let's sketch the graphs for both of these. They're both linear equations, right? They both fit the form of y equals mx plus b, where the m here was 0.19 cents. For each additional mile that you travel, we add 19 cents to the bill. In this case, the slope was 49 cents. For each additional mile, we add 49 cents to the bill. And the y-intercepts are here. Okay, so if we do like a really rough sketch of this thing, it would look something like this. Right, where this one right here represents the point 1995, and this point right there represents the point 0,3995, and there's a point right there where they cross, and this is in terms of D values. So this one up here is, which one is this one?
U-Haul.
This is the U-Haul one, U, and this one is the budget one, right? Okay, so there's the general pictures for them, the general graphs. Here's a better one. Okay, so there's the pictures, right? And as you can see, the intersect point is 66.7, comma 52.6. How do we find that point? How do we figure out that this is 66.7, comma 52.6? Well, we have our 2 equations. We have to figure out when they equal each other. So, we can set them equal to each other. So, to find this point right there, where they cross, right, we want to find out that this is 66.7. So there is some choice of D where it gives you the same result, the same cost for both of them. 0.49D. And if we want to figure out when they're equal to each other, right, find the D value that gives you the same cost for both of them, well then we just set them equal to each other. Right? So that if we set them equal to each other, we end up with 39.95 plus 0.19D equal to 19.95 plus 0.49D. Right? Figure out the D value such that both of them give you the same cost. So then we just solve this. So minus 19.95 minus 19.95, that's going to turn into 20 plus 0.19D is equal to 0.49D. Subtract 19, 0.19 from here, D, 0.19D from there. You'll end up with 20 is equal to 0.30D. And if we divide, we get 20 divided by 0.3 equals to D. And you'll see that that means that D equals to 66.7. Right, which is the answer we got a minute ago. Now to find the actual value, then the actual cost, then you can take either one of these equations and plug 66.7 and then you'll get the same result of 52.6. So for B of D, 66.7, that's going to be equal to 39.95 plus 0.19 times 66.7. So if we multiply those two together and add it to this, we'll see that this is equal to 52.6. And so the place where they intersect is the point 66.7, comma 52.6. Right, so same answer we got a minute ago. And what does it mean? 66.7, 52. So we got that right there, or that graph right there. So what does it mean? That's a sentence for that point where they cross. At a distance traveled of 66.7 miles, either company will charge you the same amount. Right? It won't make a difference whether you used U-Haul or budget if you traveled exactly 66.7 miles. Right? Both companies are going to charge you the same amount of $52.60. Okay? But now we can answer the question, when is budget cheaper? That's what we want to find out. When is budget less than U-Haul? Well, we have an equation for budget, we have an equation for U-Haul, so we can just plug those in there. So this one was 39.95 plus 0.19D less than U-Haul, which was 19.95 plus 0.49D. Well, that looks very familiar. Didn't we just solve this whole thing, except there was an equal sign there, right? But now I'm just putting in an inequality because I'm trying to solve this. Before I was trying to solve when is budget equal to U-Haul. Now I'm trying to answer when is budget less than U-Haul. So we're going to do the same algebra magic here. 1995 minus 1995. We'll end up with 20 plus 0.19D less than 0.49D. We'll end up with 20 divided by 0.30 is less than D. Or 66.7 is D. So D has to be greater than 66.7. And if we look at our graph, it makes sense. When is the blue graph cheaper, right? This one is the blue one, budget is the blue one. When is the blue cheaper than the red? Well, past 66.7 miles. Beyond 66.7 miles, the budget one, the blue one, is going to cost you less than the red one, the U-Haul one. And likewise, in the other direction, for miles between 0 and 66.7, the U-Haul one is cheaper. So which one is the better deal entirely depends on how many miles you're going to be driving. Just got to take that into consideration. If they're going to be driving a total of less than 66.7 miles, the U-Haul is a better deal. If they're going to be driving more than 66.7 miles, the budget is a better deal. Good? Good?